Hello and welcome to the second and final continuation of part 2.1 of the tutorial on writing a ray tracer in Common Lisp. The last time we had continued with our implementation of the camera, the scene, as well as the object and sphere class. We have also discussed the intersection of array and a sphere, as well as implemented the corresponding method. And finally we also rendered our first but quite ugly image. However, we still have to do quite a bit. So first of all, again, I apologize, we have to apply small corrections on the camera, only basic ones actually. Then when we've done that, I'd like to discuss and thereafter also implement the intersections of array and a cube. Thus we also need to define ourselves a cube class. When it comes to the intersections of array and a cube, we'll have to talk about the Kramer's rule as well. I'd suggest you look that up in Wikipedia too. And later on, maybe if, I think we'll get to that, we'll talk about materials and the local illumination model, the Blin-Phong shading model, or better called Blin-Phong reflection model. However, let's go and apply the small corrections on the camera so that we can proceed. As you can see, again, I've already started Slime. Now let's ASDF operate on system load up and Raytracer. And okay, here you see the thing. If you look here, Lisp complains about a missing function, W2V matrix. The reason is rather simple. If you remember, before we decided to convert the W2V matrix method here into a reader method, it was an accessor. And the last time I forgot to change this particular line here. Here we are using the old accessor method. When we, during the last time it was still in, let's say it was still in memory, or it still lived in the package, and thus we didn't get any errors. However, if we start up a new instance of Slime and compile it, now we finally get the error. All I have to do though is just to change this with a slot value cam and W2V matrix, and we're fine. The next thing, however, is a bit more erroneous. One might call it this way. If you recall the transformation of world into view coordinates, you might also remember that we not only had to multiply a given vector by the inverse of the basis transformation matrix, but also to subtract the camera's center from that vector. And this is something that I forgot here. So this really should be m minus back, and then let's see the camera position here. Camera was the camera. Okay, that's it. Control C, Control K compiles the thing. We have no errors. So that's it for this. One other thing, let's go to the scene. In the objects, our objects class provides a method called finalize. So this method is called, or should be called, we actually forgot it just before doing the actual rendering process, in order to give objects the possibility to finalize their slots, variables, whatever. This is also very necessary in order to convert between world and view coordinates. The last time we didn't get an error because of this, because our camera was at the origin, and so there was nothing had to be applied there. However, now if you look at this, before doing all this stuff like let image, delta, and zero vector, whatever, we could just say do list, and then we could say do list and iterate over all objects in the scene, scene objects scene, and then we just call finalize. We're making use of RT objects, so we can just call finalize here, and what we have is the object and the scene camera of the given scene. Okay, so maybe if you would want to render several images of one scene, then this finalize call should really be executed only once per scene. So let's introduce another slot called finalized, and we just use it to make sure that we call it already finalized. We use it to make sure that we're only finalizing once. So we say on this slot bound p the object is the scene and the name of the slot is already finalized. Yeah, that's it. Okay, so this way we make sure we're only finalizing once. Compile this. Now let's go back to the slides. We finally come to the intersections of array and a cube, and one very basic and necessary part of that is the intersection of array and a plane. However, our plane won't have infinite extents, but we'll model it like this. You can see on the right hand side I've depicted that cube here, and let us for now talk about the front face. You can see the vector p0, which resembles the origin, the lower left coordinate of this face here, and then we have two directional vectors, p1 and p2, as you could say the up vector of the plane and the right hand the horizontal vector of that plane. And however, you can express any point on this surface via a linear combination of p0 plus u times p1, so plus u times the horizontal direction plus v times p2, the up direction. Those u and v are almost arbitrary, however they are subject to the condition that u and v must both lie within a range of 0 and 1. Because if, for example, you'd say u would be, let's say at 1.5, then you would, and let v be just 0 in this case, you would end up somewhere here. So p0 plus 1.5 times p1, and this clearly is outside of the face that we want to look at. Now, you also remember the equation for the ray that we used. Every ray had a origin and also a direction. And now if we want to determine the intersection, the possible intersection of a ray and a sphere, and a face and a plane, we just set those both equations equal. And so this is the first line here. And then the next line is just a matter of bringing t times rd on the left side of the equation. And okay, this is vector-wise notation of the whole problem. So our right hand side becomes ro minus po, and we have this matrix here on the left. If now we want to solve for the coordinates u, v, t, then we just have to multiply by the inverse of the matrix, and thus bring it on the right hand side. So we solve like this: u, v, t is the inverse of the basis transformation matrix that we had here times the old right hand side, so times ro minus po. By using this u and v, just as a remark, this is also suitable for triangular faces, not only for rectangular faces, because for rectangular faces we said that they are subject to the condition u and v must lie in the range of 1 and 0, or better 0 and 1. But if we want to use it for triangular faces, we can use the same inverse matrix and stuff. We can calculate everything the same, except that now u and v are, in addition to the fact that they have to lie within 0 and 1 each, they also, their sum must never exceed 1.0. But we'll use that not before we come to meshes. Okay, as I said, we also have to talk about the Kramer's rule, because we need a way to determine how to, we need a way to determine this inverse matrix here, and Kramer's rule helps us here. As I also said, you can look it up in Wikipedia, but I think I'll make it as short and simple as possible. if you have a 3 by 3 matrix or any arbitrary rectangular matrix, but we'll use 3 by 3 matrices in our cases, the inverse of the matrix A is just the adjugate matrix of A divided by its determinant. And if you now, if we say let A be a 3 by 3 real matrix that is, of course has to be non-singular. Non-singular means just that we are able to invert it. Singular matrices are not invertible. You can just tell this by if the determinant of the given matrix A is 0, then you know it's singular, otherwise it's non-singular. So if we have a matrix like this, its determinant can be calculated very easy. It's A times E times I plus B times F times G plus C dH minus CEG minus BDI minus AFH. So that's the determinant. We'll have to calculate that. And thereafter, when it comes to the adjugate matrix, the adjugate, as you can see here, is just the transpose of the so-called cofactor matrix, and in turn the cofactor matrix is just a matter of calculating lots of subdeterminants of the matrix A. So yeah, here for this point EI minus FH, you take this AI minus FH, and if you get to the second component, you pay attention only, yeah, you strike through the first row and the middle column, and then you compute FG minus DI in this case. This is because every second element, or yeah, every second element has changed sign. Okay, however, so we'll use this to this matrix here to compute our coordinates u, v, and finally also t. We're mostly interested in t. U and v are, yeah, we need them to determine if we are really in that phase, and also later on for textures. One more important fact, if we're, this is a problem that doesn't arise with triangular faces, but only with rectangular faces. Actually, we should have some code somewhere that makes really sure that all sides here, all points are coplanar, because otherwise our equation here wouldn't be correct. There are a lot of ways to do this. For example, we could compute P2, P1, and maybe also this vector here, then calculate the determinant of a matrix where we'd use these vectors as columns, or it's, yeah, you can also do it in with a scalar product or so. Okay, just to mention it. Now let's return to our source code and let's open up a file called cube.lisp. Okay, and as always, we make sure that we are in the right package. In package CRT object, we do it just the way that we did it with the sphere. Okay, let me go to the objects file once, okay, because later on I'm sure I'll forget it, but we're going to create a cube class now, so let's make sure that we're exporting it as well. Now we go to the file cube, and hey, by the way, we really should update our ASDF system definition file. So we go into the corresponding file and say that cube now, just like the sphere, depends on lim and objects. Okay, that's it. Go back to the cube and start defining our class cube. Cube, of course, has a superclass object, and our slots will be, I'd like to pre-compute the edge points of the cube, and of those we have 8. So I'll use abbreviations because otherwise I'd have to type too much. FLL stands for front lower left, FLR front lower right, front upper right, front upper left, and of course we also have the back side, so back lower left, back lower right, back upper right, and back upper left. Okay, then yeah, that's it for now. Now we need to first of all compile this, save it, yes. Then we need a way to extend the let's call it constructor once again. Sorry for that word. We need to send the initialize instance after specialized on cube, and I'd like to introduce a few new keywords. The first one being width, height, and the last being depth. Okay, comparing too much. Now we want to make sure that width, height, and depth are always greater than 0. So we'll use assertions for that. Assert that 0 is less than width, or else say width must be greater than 0. Okay, copy that and replace with height, and here we replace with depth. Okay, when we've done that, we can start and compute our edges here, front, lower left, front, lower right, and so on. And in a few seconds we'll also be using a macro again, but let's start out without using the macro, then you'll see the reason why we are going to use the macro. We'll always have something like setf, then slot value, the given cube, name FLL, and we'll set it to a vector, make vector, a three-dimensional vector, and its initial data will be make array 3, element type is single float, and its initial contents will be vector. Now, this depends. We have the center of the object. So here we have something like, say, minus the x component of the object center. Yeah, we'll make it shorter. Let cx be the x component, the x of the object center of the cube. Cy be the y component of the center, and cz be the z component, that component. Now here we can just say minus cx. Also, we multiple times we'll have to make use of 1/2 of the width, or 1/2 of the height, and 1/2 of the depth. So we pre-compute these values. Let's say with 1/2 of the width is width divided by 2.0. We have the height divided by 2.0, and the depth is also divided by 2.0. So here we have this. Then we have cy minus 1/2 of the width, and that component of the center minus 1/2 of the depth. Yeah, that's it for just one edge. And if I'd copy this 7 times now, this would be a lot of code. So why not use a macro in this place? We say macro let. Maybe let's call it prep slot or prep edge. Yeah, prep edge. And the first thing we want to have the name of the slot or of the edge. So edge name. Then we need 3 operators. It's just always a matter of this being minus or plus. So we say operator 1, operator 2, operator 3, or no, let's call it operator x, operator y, operator z. I like that more, I like that better. So, and we'll expand to exactly this here. The only difference, now here we need the edge name. And here, instead of the minus, we need the operator x, the operator y, and the operator z. Okay. Let's see if we can reformat the code at least a little bit. This is not much. Anyways, okay, so here we have our macro, and now it's just a matter of using this macro, prep edge, front lower left, and as we had it, minus, 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 then prep edge, front lower right, this is plus, minus, minus, prep edge, front upper right, plus, plus, minus, and prep edge, front upper left, this is minus, plus, minus. Now for the backside we can just copy it and course need is we have to define our finalize method in order to adapt all those edge points, and maybe we would also want to pre-compute. I'll go back to the slides. We want to pre-compute those vectors P2, P1, as well as the surface's normal. So we'll define a few more slots. The first front, then back, left, right, top and bottom. And let's make a comment here. The following slots will assemble a list consisting of the faces origin, its up and right vector, and as well as the faces surface normal. Okay, just as a reminder. Good, so now dev method, finalize, and we can see at the very bottom the parameters were object, camera. The object, of course, is a cube, and camera. Now that's all. No need to assert anything here. What we want to do now, again, I think we'll be using a macro, but I'll start out without. What we'll do is set f, slot value of, let's say, of the cube, and the slot's name is, for example, front. We'll build a list, and the list's first element, as we said, is the lower left of that surface. So the lower left is the slot value of the cube called front lower left. Then we want to compute the up vector. That's front upper left minus front lower left in this case. And thereafter the right vector, the horizontal vector, that's front lower right minus front lower left. So m minus slot value cube front upper left minus slot value cube front lower left. That's the first one, the up one, the vertical one. Now the horizontal one, slot value cube front lower right, slot value cube front lower left. That's it so far. And last but not least, also the cross product of those two. So yeah, but instead of calculating them again, we could pre-compute them. Let's say up will be this one here, and right will be that one. Now let's use let star, and the surface normal will be the normalized cross product of up and right. So now if we set up this, we set f it to the list of the lower left point, up, right, and normal. Okay. Yeah. Again, as you can imagine, this is a lot of code. If I copy again, if I copy it 6 times, since the cube has 6 faces, 6 sides, so why not use a macro once again? Macro let's in this case call it prep face instead of prep edge. Now we have the face's name, then have its origin, its upper left and its lower right, as well as as nothing, because we are calculating the rest. Now for this to work, we need the symbols up, we need the symbol right, and we need the symbol normal. Now we can use the code that we already had and say, okay, let's expand to let. Now here precede them with a comma. This FUL is the upper left actually, so upper left minus the lower left. Here we have the lower right minus the lower left, and this is of course the cross product of up and right. Okay, so far so good. Then setf slot value cube, not front, but the face name, we use that instead. Then here the list is the origin, just replace origin with lower left here. Okay, then up, right, and normal. Okay, now we can use that macro to shorten the whole thing here. Now, as far as the front is concerned, we have our lower left is the front lower left, our upper left is front upper left, and the lower right is front lower right. Then let's make a comment here. That's the front. We don't need that comment because the name says it. Front. Then we have the back, and the back is let me think. The lower left is the back lower right. Then the upper left is back upper right, and the lower right is the back lower left. Then we have the left, and there we have the back lower left, back upper left, and front lower left. Right side. There we have the front lower right, front upper right, and back lower right. Now the top, and the top, there we have the front upper left, back upper left, and the front upper right. Let me once again think. There we have front upper left. This should be our front upper left will be here. This should be our origin. Then the back upper left, yes, and then the front upper right, yes. Okay, that's fine. And finally the bottom. And the bottom, there we have the back lower right, then the front lower right, and finally the back lower left. Okay, and yeah, again, we should maybe return T. Compile it. Now we get some warnings here. Let's see, why is that? Slot accessor is undefined for something. Somewhere I have used, I forgot a comma, I suppose. Yes, here. So this should be a comma. Compile it once again, and the error is gone. Okay, yeah, so far so good. Now we should go ahead and implement the method that we used, to finally calculate this stuff here. All that we did up until now was only pre-computation, necessary pre-computations. Now let's go ahead and implement also this stuff here. We do it in objects.lisp because, as I said, we're also going to use that for triangular faces, not only for the rectangular faces of our cube. So let's call it defun intersects face, and our arguments will be the face's origin, its vector, its up and its right vectors, and of course the ray. Now, if we look at this, I've substituted the elements of the matrix with the letters A, B, C, D, E, F, G, H, and I in order to make the rest even easier. We'll do the same, the very same here. Let's start. A is the X, yeah, okay. If you look at this matrix here tells us that the first column is P1, the second is P2, and the third is minus the ray's direction. So A is minus the X component, is the X component of P1, B is the X component of P2, and so on. So this is the up, or no, the right vector. Then we have B, and this is vector X of up, and C, that's minus the X component of the ray's direction. Okay. Then actually I could go ahead and copy this, or I could not copy this, copy it. Now, there we go. So D, E, F, G, H, I, and here we have to exchange X and Y, here X and now the next thing that we can do is calculate the determinant. We need that in order to determine whether this is invertible or not, whether there is any intersection of the plane at all with the ray. Actually, the only case where we wouldn't have an intersection would be if the ray's direction would be coplanar with the plane. So now we have to compute the determinant AEI plus BFG plus CDH and so on, as I said. Let's do it. Let me shorten it here using abbreviation det. There we have minus, plus, and there we have AEI. There we have BFG, and there we have finally CDH. And this is minus CEG, minus BDI, and minus AH. Okay, before we continue, the first thing we want to do now is we want to check whether the determinant is not equal to 0. So we do that, or else we return just nil. And if it isn't, then okay, we could, let's see, then we really should compute the dot products. All the results u, v, and t, u, v, and t are just a matter of computing the cross products of either row here with the right hand side of the equation. The right hand side is RO minus PO. We like to pre-compute that. So the right hand side is minus the ray's origin minus the plane's origin, so minus origin. That's it. Star. Okay, then we have u and u. Now let's look. We have EI minus FH, that's the first component, so plus this, there we have minus EI minus FH, okay, times the x component of the right hand. Then we have CHVI minus that plus the y component of the right hand side, and then finally BFCE, the z component. Okay, like that. And to copy that, then we have V. This is FG DI, then AICG, and then BG AH. Make that sure once again. Okay, it's in the wrong row. So let's check that once again. EI minus FH here, then CH minus BI. Okay, and then BF minus CE. Okay, then FG minus DI, then AI minus CG, and then CD minus AF. Okay, there's the arrow, minus AF. Okay, then DH minus EG, BG minus AH actually, and AE minus BD. Minus BD. Okay, again we could use a macro, but I'm just too lazy to define another macro now. We have all that we want, and in this case we return multiple values. This is faster than returning a list, and because we don't need to cons up a list. So now here we have multiple values being, of course this is not u but the distance. This will be the first, and u and v. Okay, that's it for intersects face. Let's compile this file. Then we'll go to the cube and see what we can do to calculate the intersections. So we have method intersects. We'll need another one of these. So the object is of course a cube. Then we have the keywords lower bound, the default value of 0.0 and the shadow feeler. Okay. Since we're first not going to use lower bound and the shadow feeler, I'll first just ignore them. Lower bound and shadow feeler. And now, okay, what I would like to do, we have the 6 sides of the cube. I'd like to construct a list of the intersection points and then filter out the most suitable intersection point. So we might want to do something like let intersection points, and we want it to be, this is, yeah, we could for example use the loop macro here. Let's see, loop, then for side in, the sides are front, back, left, right, top and bottom. Now we, let's say that for IP, this will be our current intersection point, for IP equals now multiple value bind, or no, first of all we need a destructuring bind here, because our slots are really lists, whose first element was the origin, then up and right vector, and then the face is normal. So let's say destructuring bind origin, up, right and normal of the slot value of a given cube with the name side, and of that we'll calculate the intersection points, multiple value dist u and v of intersects face, origin, up, right and a given ray. Now okay, if we have that, we say when dist, because it is of course possible that dist is nil if there is no intersection, when dist we cons up here, let's say make a list of, yeah, what does our intersects method usually return? It usually, let's go to the sphere to make sure, we return the closest intersection distance, then the object, and then the point on the array. So we'll do the same here. We build a list of dist and of the object, which is of course the cube, and finally the point on array, array and dist. Let's first forget about u and v, returning them here. However, yeah, okay, I just finished that, and then again there is a little problem. Now we say unless IP is null, we collect IP. This should give us a list of intersection points. Turn it here so that we can check it. Now I just once go back to our intersection method. As I said, we want to test for not only rectangular but also triangular faces. So why not introduce a test function? And here we now say when funcall test fn of u and v, if this returns true or t, then let's compile it. We finally return the values. Go back here. Now what we need here is we need to provide that test function, say lambda u and v, and we wanted to have to make sure that and 0, u and 1, as well as v is also between 0 and 1. That's it. Compile the file, no errors. Now we have warnings here. This is, yeah, I bet it's related to u and v being never used, and as well the variable normal is defined but never used. yeah, we could. I will not use them until we come to the part of lighting. So yeah, let's just forget about that. Go to the REPL, use package linalg, and now let's go ahead and define ourselves a camera. Make camera. Sorry, dev parameter. Camera, make instance of the camera, and the position is just the origin, make vector 3, and the up vector is make vector 3, data, 3, and data is 0 this way, and we look at far away again, make vector 3, data 0.0, 100.0. That's it for the camera. Then let's define our cube. Make instance CRT cube objects. Sorry, cube whose center is at the point we're looking at, and whose width, height, and depth are all 20.0. Okay, there we have our cube. Let's go ahead and inspect it, just, or at least one or two variables to see what it looks like. Of course, the sides are unbound, but so are back upper left and back upper right. That's something that we do not want. So let's see what happened here. Of course, during the copy and paste, yeah, one should really avoid copy and paste. I used the wrong symbols. So now we go back, define the cube once again, and now let's see, inspect it, go here. Now we have everything bound but the sides and the material. The material is okay, we don't need that right now. Now let's see, front lower left should be -10, -10, 90 exactly. We go back just by hitting L, and let's look at the back upper right, for example. That's 10, 10, 110. Yeah, nice. That's all that we want. Now we need to finalize the cube. Say CRT objects finalize the cube and the camera. The variable camera is unbound. Yes, because we called it cam. Now it returned T. Let's go ahead, inspect this object once again and see, for example, the front side. So I go to this list, and yeah, I see that it's comprised of 4 matrices. The first one is the lower left. That's okay for this here. Then we have the directional vector, the vertical one. That's also correct. Then we have the horizontal one, and yeah, that's fine. That's the surface normal. At least for this side, we can say that everything worked as we wanted it. Now, for the dissection test, we need to define the array as well. So we make an instance of array, CRT array. Its origin will be just the origin of the coordinate system, and its direction will be a vector of dimension 3, and we'll just look along the z-axis. Now let's see if we call intersects on the cube and the array without a lower bound or shadow feeler, what it returns nil. That's not nice. Go to objects. First thing that I really forgot, I said, let's go back to the slides, we had to divide the outcome by the determinant of A. Since we have made sure that the determinant is not 0, we can safely do it here. So we divide that by the determinant. No, not the right hand side. Sorry, that's not correct here, but this. So we divide this by the determinant. Then we go here, divide this by the determinant, and also the dist. That by the determinant. Now let's compile this. See, we get an error. is malformed. Okay, why is that? This one is correct. This one is correct. No, this one is actually not correct. It should be something like this here. So this is correct now. Here we have v, divide that by the determinant, and also here we have the distance, and divide that by the determinant. Compile it. Now let's see what happens. Now this looks really good. So our only mistake was that we didn't divide by the determinant. Here we have 90.0 and 110.0. That's exactly the z coordinates where the axis aligned faces are at right now. We could now go ahead and define another vector, say it's another array, say its origin. We're at let's say 100.0, 0, 0, and now at where the cube lives, and its direction would be -1.0, like this. Here, compute the intersection again. Okay, of course we get the same values. However, we have now tested against the left and right side of the cube, not the front and back as we did in the first example. And finally, we'll do the same with the top and down sides. So here we need this. And again, we get intersection points. Nice. That's almost it. However, we still, let's go back once. We have a list and we have 2 intersection points here. We want to determine the correct one. When we computed the intersection points of the array and the sphere, we used this min in range function. Now we would like to use this min in range function for the intersection of, let's go to the cube, of the array and the cube as well. Right now we just returned all of the intersection points, but actually I would like to return only the one that fits. So the difference is when we used minimum in range, let's see, what did we use? Yeah, we applied we used it here just to determine the minimum of the real value of the distance. Now we already have a list whose elements are lists itself. So we need another way to access the elements or to determine the minimum element, which is why here we need another keyword called key, and which will default to the identity, so that we can also use the min in range like we did with a sphere. And now what we have to do, we have to remove certain elements, but the check here is with the given key. So key is key, and then we cannot use apply anymore. Instead we have to use define our own function. There we could use reduce, define our own function lambda ij, so our a b, like the elements, and there we'll say if fun call key a is less or equal fun call key b, then we'll return a or else b. This should do. Let's compile it. Of course, now what do we have here? The variable ELTS is defined but never used. Yep, we should really use it. Let's do this, compile it, go to the REPL and see what it's like. So in package CRT objects. Now we're in that package. And min in range. Let's see if it works as it worked before. Like this. Here we get 1.0, then we say the lower bound is 2.0, we get 2.0. Now we have the case where we have a list like this. Okay, or 2.0.p, 3.0.z. This is a dotted list. We could make use of any list. Now we say that the key is the car. Let's see. Okay, and this is exactly what we wanted. We did not only want the 1.0 but the whole element 1.0.a. Now we also use the lower bound 2.0, and it still works as expected. Very nice. We go back to the cube and make use of exactly that. So we say in range, and our elements are the intersection points, of course. Now our lower bound, like this, lower bound is the given lower bound, the upper bound is the provided shadow feeler, if any, and the key in our case, since the first element of every list here is the distance, our key will be the car. Let's see, compile it. Again, what do we have here? First of all, this reading an ignored variable. Thank you for that hint. We have to remove that declare statement. We got rid of that. Now this is again, I bet, about the normal and u and v. Yes, okay. So since we're going to need them anyways, I'll just return them, u and v, and the surface is normal. Let's compile this, go back here, and go back to the CL user package, CL user. Cannot be coerced to a string, no it can't, but this one can. And do our intersection test once again. Yeah, very nice. We only got the one that we wanted. 0.5, 0.5 looks very good for our case too. Here I hope we have the normal, and yeah, this is the closest, obviously the closest intersection. Nice. So why not go ahead? Let's go back to scene.lisp once again. Now we could see if we can render a scene. I would like, since we're going to render a lot in the ongoing minutes, let's define a file called simple scene.lisp. Simple scene.lisp. Okay, where we just define the first thing, the parameter, the camera. The camera is an instance of CRT camera. Its position is vector 3. We want to experiment with that a bit, so I'll use a vector 0.0, 0.7. Okay, this is at first the origin, but that's okay. Now it's up, is this here, and then it looks at the position 100.0. Okay, so far so good. Now we also need a scene, say make instance CRT scene, and we have the parameters camera, which is cam, and yeah, nothing but the camera. Okay, that's it. Then let's say we have a cube, make instance CRT cube, and the CRT objects actually cube, and its center is at 0.0, as we had before. Its width is 20, its height is 20, or let's make it 40, and then it's getting a little bit bigger, and its depth is 40 as well. Okay, now yeah, if I say define render, we can also make a package for that here, dev package simple scene, and we make use of a lot of things actually. We make but this time the CL package here is enough. What we export is render. So here we say render, we don't take any arguments right here because we are going to use CLRT scene render. We'll render the scene 640 by 480. Our file's name will be test PNG. That's it. Compile it. Okay. Very anxious that this is working. Simple scene dot render. Now let's see. This function is not defined. Why isn't it defined? It should be simple scene render. We're creating the package here, and we're exporting the symbol render. Simple scene render. No, this is really weird. Yes, it isn't actually, because as usual I forgot something like the in package here. Now the function make vector is undefined. That's also clear. Let's just use linalg and we're done with that. And of course now we have a lot of symbol conflicts. We'll resolve them as correctly. So linalg. Oh, this was actually the only one. Shadows the following symbols. Yes. Let's add unintern make vector from simple scene. Now recompile it. Yes, everything is okay, and go ahead and render. Okay. Next thing, we should provide ourselves with a completion percentage, output, whatever. Let's see what our image looks like. It looks very bad. It looks black. Okay, that's not what we wanted. However, to see if it works like it at least worked last time, let's define a sphere as well. Make instance CRT scene sphere, and the sphere center is also at. I'm so sorry. I'm more than stupid. Of course, after creating the cube, we should also add it to the scene. So add object scene cube. Let's compile this once again. Let's go back. Invalid number of arguments 0. Where was that? Once again, compile it. Here. Where I'd find the closest intersection, lambda. Okay, so in the objects file, min and range, of course, we should, before using reduce, we should even check if there is an element in the list at all, like this. Okay, and render the image now. Okay, at least it seems to do something here. And it takes quite long. This is not due to Lisp being slow, but our implementation being rather slow, however readable. Open test PNG, yeah, okay. Unfortunately, preview always opens the image on my other monitor. However, you see, yeah, that you just see a plain rectangle, but that's the cube seen from the front. So we have that also. Yeah. Okay, let's close that here, that window, and return to the source once. Yeah, we have all that. Now, as I have already, before we go to the lighting, as I have already used the U and V coordinates and returned them as here, let's go to the cube. Here we are returning them, the normal U and V. Let's say, yeah, why not also do this right now with a sphere? Actually, I don't know by heart how to compute U and V for the sphere. I have to look that up, but I know how to compute the normal. The normal, of course, is just the normalized vector of the intersection point minus the sphere's center. So here we can say we return, yeah, what do we return? Let's return nil and nil for U and V, and I'll do that on a separate line. Make a to-do here, and then we return the normal point array t min. Okay, that's it. And then the normal is okay, this looks better. The normal is normalized. M minus the okay, the point on ray is actually the intersection point, so let's only compute it once. Let IP be the point on ray t min. So here we can say IP, then nil nil, okay, and minus the normalized version of M minus IP minus the object center of the sphere. However, this is called C already, so we use C. Compile this once again, we're done with that. Okay, good, let's go back to the slides and continue talking about the Blin-Phong shading model, which should be actually better called the Blin-Phong reflection model. The Blin-Phong reflection model is basically an extension to the Phong reflection model, which was invented in something like 1975 or so. The Phong model is an empirical model. It's physically incorrect actually, but anyways it delivers nice results. It is physically incorrect in terms of being, for example, not energy preserving. What the Phong reflection model does is basically just, we talk about the incoming energy of light and the outgoing energy of light at a certain point at the surface that we are currently dealing with. And what it does is that it splits the outgoing energy into three distinct parts, the first one being the ambient, and then the diffuse, and then also the specular part. The diffuse part is related to something called Lambertian surfaces, whereas the specular part is just something in terms of pure reflections. However, if you look at the next line, what we'll be doing once we have an intersection point and we have ourselves defined some lights, we'll be initializing the outgoing energy, or in our case the outgoing the color at a certain point with the ambient energy, and thereafter we'll iterate over all lights in our scene and add up the related diffuse and specular parts of that light, depending on a few more vectors that we have to calculate, like L being the direction to the light, N, as we know, is the surface's normal. Then we have the vector V, which is the direction to the viewer. In our case, this would be just the inverse direction of the incoming ray's direction. And then we have this vector R here, which is just related to Phong. We won't be using it in the end, as we'll be using Blin-Phong, but just to tell you what it is, R is the ideally reflected direction of the incoming light's direction. And since this is, as I've denoted here somewhere below, as this is somehow expensive to calculate, it's not complicated, but it's expensive in the end. This is why Blin-Phong finally came up with the idea of using a so-called halfway vector instead, and measuring the angle between the halfway vector and the surface's normal. I also have to add that those parameters, those constants K ambient, K diffuse and K specular, are empirically chosen. Once we have defined ourselves a material class, we'll see to that. We'll have these constants defined there. They are, however, subject to the condition that their sum must be exactly 1. So that at least we get into the direction of being energy preserving. And then there's also, I forgot this, there's this constant alpha, and alpha is used to describe a surface's the surface's roughness. If you can imagine, so let's once get back to Phong. Phong says that most of the light that is reflected on a surface is reflected into that ideal reflection direction, and so this is why he measures this angle between the viewer and this ideal reflection direction. And if you, this dot product is what is in for us it's a matter of of a value between 0 and 1. In the end, the result is between 0 and 1, and you can imagine that if, for example, we have something like the result of r dot v would be 0.6, 0.6, and if alpha, I think 50 or so is a reasonable value for that. If we take 0.5, 0.6 and raise it to the power of 50, that we will end up with a pretty small value. So the higher alpha is, the harder the surface is, and the smaller will be, or the thinner will be, the reflected light point that we'll see on that surface. So for more diffuse and rougher surfaces, this will be a low value, and for harder surfaces, this will be a higher value. Okay, so here, as I said, Linfeng makes use of the halfway vector. We'll see that on the, not the next, but the one thereafter slide. Okay, in the end, this line here is just exactly like the equation that we had here. The only difference being that instead of r dot v, we now use h dot n. So the last line here, the selected line, is exactly the Linfeng equation. Let's go to the next slide. I have mentioned the Lambertian surfaces, and yeah, let's talk about Lambertian reflectance. When we're talking about Lambertian surfaces, we're talking about diffuse surfaces, and what Lambert once said was that yeah, the luminance of light is a matter of the luminous power of the light divided by the illuminated area. And if you look at this graph here, you can see the incoming light's direction. This is minus L. SL in our case will always be the direction to the light, but since I've denoted it here vice versa, this is minus L. We have this, and we have the surface as normal. And okay, first of all, of course, the rays of light would never be parallel, as we're not talking about laser rays or something. Anyways, for our idealized model, this is quite okay. So if you imagine the light coming in from here, and if you now also imagine that the luminous power of the light would be somehow depicted as this A here, as the area A, you can also see that the more the light's incoming direction would be bent towards the surface, the more it were rotated in that direction, the bigger this area B, the illuminated area, would get. And alpha is just the angle between the surface's normal and the incoming, or not the incoming light's direction, but the direction to the light. And this alpha is of course the same. So to calculate here the cosine of alpha, this is just a matter of dividing A by B, or in our case taking the dot product of n dot L. Okay, so far about the Lambertian reflectance. This is the thing that we used for, or that we are going to use for the diffuse part of our Linfeng reflection model. And for the specular part, we'll have, I've made this graph here just to show once again the difference between the halfway vector and the vectors r and v. So what Fong basically said was that most of the light, here we have the direction to the light again, here we have the direction to the viewer, this should depict the viewer here, that most of the light is reflected in the ideally reflected direction of the light's vector. So this would be around this vector here, most of the light would be reflected into this direction. And Linfeng changes this and says that he wants to use the halfway vector instead, which is this h vector here. As you can see, this is exactly on half of the way between v and L. And he measures not the angle between r and v as Fong does, but instead uses the angle between h and n. Okay, so let's go back to the source and maybe start out with defining with creating a light fire. I call it lights, although we'll only be dealing with point lights. Of course, it's quite easy to define also area lights and stuff, but as Phong and Blin Phong are related to points light only, I think in our case it's sufficient to deal with point lights, with only point lights. So we have this lights file. Again, I defined a package for that called clrt lights, and we'll be using CL. We'll also be using the linalg package here. Okay, let's make sure we're in the right package. And now, before we forget it, update our ASDF system definition. Here we have lights, and internally depend on linalg. Let's see, in the end also we'll be needing the lights for the scene, so the scene now also depends on lights. Go back to the lights and define class light. So, and the slots will be every light. What does a light have? It has a position and it has a color. Now we'll provide an init argument for that. Init arg will be the position. The init form will throw an error if the position isn't specified. Of course, it must be specified. Then the type will be matrix. Yeah, and of course we also need a reader. Let's call it light pos. Now let's talk about the color. Init argument will be color, and the init form. Yeah, I'd like to just let this default to white. So we'll be using vectors, just the three-dimensional vectors for the lights, where the components resemble the red, green, and blue components. So the we'll use make vector 3, and data will be 1.0, 1.0, 1.0. Up until now, we have used byte values between 0 and 255 for the colors. However, for now or from now on, I'll be using floats. Later on, we'll have to make sure that they are converted to bytes, and of course that before they are converted, they do not exceed 1.0. So this is also of type matrix. I need a reader for that as well. Light color. Okay. Shouldn't forget to export the symbols as well. First one being the light class, then the light position and the light color. Okay, let's compile it and see. That's nice. Okay, then we also, let's get back once again to the slides. We of course, in addition to the lights, we need some way to define a material, especially those constants that we were talking about, kmp, diff, spec, and the roughness, as well as the diffuse, specular, and ambient colors of the material. So let's introduce a material file here, material.lisp. Again, package for that, clrt material, and we'll be using cl and linalg again. Yes, okay. So export the symbols later and package clrt material. Now dev class material, we have again no superclass, but yeah, we have the ambient color, then we have the diffuse color, and we have the specular color. Then we have the ambient coefficient like k ambient, then the diffuse coefficient and the specular coefficient, and lastly also the roughness. Okay, now we'll initialize those slots. We'll provide an init argument, ambient color. Maybe we'll let this default make vector, make vector just to black. The type will be a matrix, and the reader will be called ambient color. Okay, so I could just copy that and then replace ambient with a string, ambient with diffuse. Again, replace string, ambient with specular. Okay. So we have that. As far as the coefficients are concerned, again we provide init arguments and coefficient. Now let them default to 0.0, and the type, yeah, okay, we'll make use of the fancier type declaration of Lisp, where we say that this is a real value between 0.0 and 1.0, so that Lisp checks this for us, and the reader will be called ambient coefficient. Okay, again I'm going to copy that. Now and replace string ambient with diffuse, and again replace string ambient, this time with specular. Now we have that, and we still have to deal with the roughness with this parameter alpha. The argument will be roughness, then our init form. I said reasonable value would be 50, so we just let it default to 50. The type will be integer 0, so we only have positive integers including 0, and the reader will be the roughness. Okay, let's not forget to export those symbols. Export the first one being material, then we have ambient color, diffuse color, specular color, ambient coefficient, diffuse coefficient, and specular coefficient, and finally also the roughness. We'll need parameters like refractive index and so on later, but we'll get to that as soon as we'll talk about reflections and refractions. One more thing, maybe I'd like to let a material default to black. Yeah, it would be okay. However, why not just let it default to white, the diffuse part at least. So maybe this way here, or no, maybe it's faster if we use make array 3, and the element type will be single float, and the initial element will be 1.0. Okay, so then we should adapt the init form for the diffuse coefficient as well. Fine. Okay, now go back once again to the slides. We have to make sure, we have to assure those side condition here that kamp, diff, and spec add up to exactly 1. We'll use initialize instance for that after, and we'll specialize on the material. Don't forget the key word here. So now we want to assert that the sum of the ambient coefficient of the material, the diffuse coefficient of the material, and the specular coefficient of the material is exactly 1, or else say that the ambient coefficient, diffuse coefficient, and specular coefficient must sum up to 1.0. Okay, then let's compile the file. No error until now. So that we have that. By the way, update our system definition file here and add the material. Okay, file material depends on linalg as well, and we'll make use of the material in the objects. So we have this here, and later on we also need it in the scene package. So we have that. Then let's head to the objects file, and up until now we haven't specified a type or something. We didn't even provide a init argument for the material. We'll do that now, right after using CLRT material. Now we say we have an init arg for material. We now assure we now need a material for every object, so material must be specified. The type is material, and the reader stays the same. So far so good. Compile that, and let's see. We have name conflicts that we have to resolve in favor of CLRT material. Do that. Okay, let's once again compile. Here we're still exporting that symbol. So unintern material from CRT objects. Yep, go back, compile it. Why do we have still, oh yeah, from CRT objects. This should work actually. Let me see if we have something, a symbol material here that we really shouldn't have. Right now I don't see it. However, this is no problem. Let's continue, yeah, go back to the slide so that we see the equation that we are going to compute. Let's go back to our scene. And there, yeah, we now need CRT material as well as CRT lights. Make sure that let's call it CRT lights. Yes, I did. And oh, you know what? Also forgot CRT ray. Anyways, we're using it, making use of the ray, for example, yeah, somewhere here. Yeah, there we are making use of the ray. So yeah, we've preceded it with CRT ray. Yeah, so yeah, that's okay. We don't need that. We don't need to make use of that. So now we have that here. Since now we are dealing with lights, we need a way to add lights to the scene as well. Push light slot value scene lights. That's it. Don't forget to export the symbol add light. And then let's see. Oh, one other thing that I just see. We said that we wanted to make sure that the scene is only finalized once. This is why we're checking whether the slot already finalized has already been bound. However, we should also set the slot. So use prompt. Here we are iterating over the objects and then make sure that the slot is actually bound to something. So slot value of the scene, the name already finalized. Yeah, we just bind it to T. That's enough. Okay, so that is solved. And yeah, then let's go to the trace ray function and let's see what we can do about that. Okay. Now we have to calculate all this stuff here. Then, yeah, at first we should see the closest match. As we know, is list with the elements. The first one being the minimum distance. Then we have the object. Then we have the point on the ray, the intersection point. Then we have the coordinates u and v as well as the surface normal. So do a destructuring bind on the expression closest match on that variable, and with those values we can go on and calculate everything. Then yeah, we want to we might want to get hold of the object's material. Let's say that will be the object material of the object that we have there. Then let's initialize the color. We'll use that variable to return the final color in the end. Let's initialize it with the ambient color of the object. So we have to use m star of the ambient coefficient of the material and the ambient color of the material. Now that we have that, I don't think we need the star here. We can iterate over the lights and see what we can do now. So we say to list light, and the list will be the slot value of the scene with the name lights, and in the end, what will we return? We'll return the color. Okay. Now for every light, we have to compute some things. First of all, the direction to the light. The to light is just m minus the light position of the current light, and m minus the intersection point. Then for the shadow feeler, we'll need the distance to the light. So let's say dist to light is the vector length of auxiliary direction to the light, and the final direction to the light is the normalized version of that vector, so auxiliary to light normalized. Okay, now that we have that, we can go ahead and for the diffuse part calculate the dot product of L and N. So let's say alpha is the dot product of our normal and the direction to the light. Doesn't matter if we take dot normal and dir to light or dot dir to light and normal. Do it this way. Then let's also calculate this halfway vector as well as the dot product of this halfway vector and n, as we need that also. So halfway vector will be normalized version of n plus the normal and, oh no, actually not the normal, but the direction to the light plus the inverted ray direction. So inf ray direction is m star minus 1.0 times the ray direction of the ray that we have. So here we have m plus of the inverse ray direction plus the direction to the light. Okay, this is our halfway vector, and I'll call that the result of h dot n, I'll call that beta. So here we have the dot product of the normal and the halfway vector. Okay, then now that we have that, we can check whether the result of alpha is greater than 0. The maximum value will be 1.0 anyway, since we're computing the cosine of the angle, and we don't want to be that less than 0, because this would mean that we'd be in the lower hemisphere, but we are only interested in the upper hemisphere. So let's make sure that alpha is bigger than 0, and if it is, then we'll increase the color. We'll say, okay, ZF color, ZF color, and we'll have to increase that. We'll have to say M plus, and plus the existing color, and now we have M star of the diffuse coefficient of the material. Diffuse coefficient, let's go back to the slides. Here, this coefficient, diffuse coefficient of the material, times, what we now need, we need a way to do an element-wise multiplication of the light's color and the material's color. We don't have that right now, so let's just right now jump to the linalg package. And if you remember, when we defined m plus and m minus functions for that, we did this by defining first a macro and then making use of that macro. Now we can use that to have an element-wise multiplication of two vectors or even two matrices. Let's call it m dot, and our operator will be just the product. So we should also export that, compile it. Okay, go back to the scene file. since now we want to multiply the color of the light color of the current light and the diffuse color of the material. Okay, this is it for that. And then, so this is the part that we had here. We have multiplied, I diff actually is the result of the element-wise multiplication of the light's color and the material's diffuse color, and we'll multiply this with the diffuse coefficient and then add this to the color. And okay, better, we need to not check if this is above 0, because it will be, no it won't. We also have to check if beta is above 0, make sure that the angle is correct here, and then set of color to m plus, then the color m star specular coefficient of the material times let me think, times the specular color of the material times the light's color element wise, so we have that. But anyways, we also the result of h dot n, we have to raise that to the power of the roughness. So here I even forgot those parameters. Here we have to insert alpha as well. This is also good. We could make use of mult here. So we multiply alpha, the diffuse color, and this thing here. We have the same here. We'll be multiplying not beta itself, but beta raised to the power of the roughness of the material, as well as the specular coefficient, as well as the element-wise multiplications result of the element-wise multiplication of the light's color and the specular color. Okay, I think that's it so far. Or here we have the case first, the first case where we have a closest match, and if we don't have one, we might just want to return a black vector. So let's say make vector 3. This is completely black. Now, maybe we could make a little bit more intelligent use of ZF here, since in the end we return, I'll just leave it the way it is right now, and later on we can deal with that. Now, as now we are returning a vector, a color vector, and not a list anymore, and also we don't return byte values but floats instead. We have to adapt our ZF of the point in the image plane. So now, first of all, we want to use the first component of the returned vector as the red component. So we say vec x of color. Then we have to make multiply it by 255, so that we scale it correctly, but also have to make this a byte. And finally, also make sure that this doesn't exceed 255. So we end up with this expression. Here, this is almost the same. M star 205. The only difference being that now we are using the y component as green, and here minimum 255 truncate M star the z component. Okay. Now let's close this. We get a lot of style warnings. The variable object is defined but never used. Where are we? Okay, all the errors or warnings are related to traceray. Then let's see here. The variable dist is defined but never used. Yeah, this may be, and u and v aren't used either, so we can just say and declare ignore dist view int v. Okay, let's compile this once again and see here, undefined variable mat. Okay, so we in fact need the star. Just compile it once again. The variable dist to light, no, it is still to light actually, and not dist. Oh yeah, there we have the distance. Okay, that reminds me of something. We have to make use of the shadow feeler. So when we iterate over the lights, first of all, maybe even before we are calculating all the stuff here in the inverted ray direction, alpha and beta, and so we might want to, or no, we not might want to, but we actually want to determine if there is an object between the intersection point and the light source. And if there is, we don't need to add color from the light, because this is the light is occluded by the object. So let's say unless find closest, how did we call it? Unless find closest intersection, and yeah, scene. Now we have to construct array, make instance CLRT ray, and its initial position will be IP, our intersection point, and its direction will be the direction to the light, still to light. And yeah, okay, we have that. Then here, find closest intersection, our lower bound now. Yeah, let's use something like 0.01 or so to avoid numerical problems. And as the shadow feeler, now we use the distance to the light. And unless we find something in between, we can go ahead and make all this computation here. Okay, unless this. Here, yeah, we have to use another let of all those things here. I have to see if the parents are okay. Yes, here they are. We're only doing this if there is no intersection. We're adding up the color. Yeah, that's it. Okay, compile this. Still have some style warnings. The variable inverted ray direction is defined but never used. Yeah, again, let star, and let's compile it again. Now undefined function ray direction. This is due to the fact that we haven't imported, haven't made use of CLRT ray. Okay, so let's just do it. In this case, we can get rid of, let me see, wherever we have array. Here we can get rid of all those CLRT rays now, and just say make instance of ray. And so here as well, don't have any other occurrences of that. I'll compile the whole file. Of course, now we get name conflicts, resolve the name conflict in favor of the CLRT ray, and again in favor of the CLRT ray direction. Now where is that? The variable object is defined but never used. Here we also have something, because this really is the light. Compile it. Now, yeah, of course, CLRT scene also shadows the following symbols. Ray direction, let's go and unintern it, unintern ray direction for CLRT scene. Go back to the source, compile it. However, we still get that here. That's the same problem as we had with CLRT objects, and I think it was matrix or so. Okay, anyways, it compiles. Now let's go to the simple scene, and yeah, we need a material now. Let's set that parameter blue material. make instance of CRT material, and we'll initialize the ambient color with make vector 3 data will be very dark blue, and the ambient coefficient, something like 0.1, that's sufficient. Then the diffuse color will be slightly brighter blue, 0.8 or so, and the diffuse coefficient will be, say, 0.6. Then let's use specular color, make vector 3 data, and this will be just white. And the specular coefficient, now since we already have 0.1 plus 0.6, we only have 0.3 left. Okay. Yeah, and the roughness, let's try out 50. Now the cube also needs material, so let's initialize this with the just create blue material. Let's compile the file, and let's see. Let me just go once again to the cube, because I have here exactly when we wrote our finalize method, we forgot a very important thing. Already had that in mind, because of course before doing all this we also have to transform our edges from world to view coordinates. We simply forgot that. So let's say do list, and this will be the edge. We'll have FLL, FLR, FUR, FUL, BLL, BLR, BR, and BUL. And for all those edges we have to call set F, slot value cube edge, and we'll be doing world to view of the given camera, and the slot value cube edge. Okay. This was quite an important bug, I think. Yeah, let's see, let's compile this. Let's go to the simple scene, let's compile this, and maybe try to render it. Simple scene, render, and yeah, let's see if it makes any sense. The image takes quite long. The speed will improve as soon as we'll be using axis-aligned bounding boxes, and okay, open test PNG gives us a completely white image. This is of course not what we want. Let me go back to the source and see why this might be the case. Let's go to the scene here. Okay, we're initializing the color with the, here we are, we're initializing it with the ambient color, and here if closest match, and in the end this do list returns the color in the end. Then we compute all the stuff here. We have the ray with the direction to the light, and see if there is something in between, and if there isn't, we continue calculate the inverse ray direction as the direction to the viewer, so to say. Then alpha is the normal between the direction to the light and this here, and the surface is normal. The halfway vector is the normalized result of adding the inverse ray direction and the direction to the light. This is also okay. Then beta is the dot product of the normal and the halfway vector. This is also okay. Here we make sure that we are in the upper hemisphere, and if we are, we add to the current color the result of alpha, the coefficient, times the diffuse coefficient of the material, times the result of the component-wise multiplication of the light's color and the diffuse color of the material. Okay, this looks good to me. Then here, if we don't have a closest match, we just return black. So let's see if here is an error. we are multiplying, color is the result of trace array, and we are multiplying it with 255, then truncating it, thus converting it implicitly to an integer and maximizing it with 255. The use of min is absolutely correct here, because we want to have a lower value. Okay, let's go to the scene and see if we've made an error here. Yeah, maybe. Okay, our camera should be here. I have to just render it once again and see if this was just due to a mispositioning of the camera. So, yeah, as I said, or as you can think, that this is quite slow. It's not related to Lisp, but due to our implementation. However, if we told Lisp to get rid of all our assertions and to optimize for speed, we get a lot of speed improvement. Okay, however, the image is still white. Okay, so what I'm going to do now, I think, because this is quite boring for you, if I'm hunting down the error, I'll make a break here and see where the error lives and then explain it to you later. Okay, I'm sorry for that. Now here, let's make a cut. Okay, welcome back. I finally managed to find the error. It was quite deep down. You see here, if I scroll up, that we are using m star, 255 times the first component of the vector. First of all, there's no need to use m star. Instead, we could just use the normal star, the product function. But however, the error is related, or was related to m star. Let's go back to the linear algebra package and see what the problem was. Yeah, here it is, and by now looking at it, it can be clearly seen that this should actually be a star and not a plus. I could hit my head on the table for that. This was the straight punishment for not testing this function. Basically, this was the only function that I never tested of the linear algebra package, and now there it is. Okay, so we've exchanged this plus sign with a star. Compile it again. Let's go back to the file simple scene now. Here, of course, there is another thing. We haven't added a light to the scene, so I assume it would be rather dark in here. Now, let's say we have a light, make instance of CLRT lights, and its position will be like vector 3 data, let's say minus 100, 100 and 0. Okay, we have that. We let it default to white, and CLRT scene add light scene light, add it to the scene. Okay, now there's another thing. We go back to the scene, and okay, first of all, we can get rid of the m here, because this really isn't necessary, as is the multiplication with a real value. So now here, where we construct the array, make instance array, in fact the keyword to initialize the origin of the array is origin and not pos, so we have to exchange that as well. And last but not least, I would just, to have it really complete here, insert an assertion that before we start the actual rendering process, there are lights and also objects in the scene. So assert consp of slot value of the given scene and objects. This asserts that this is a non-empty list. There are no objects in the scene. Okay, this is the first one. Now we'll do the very same with the lights. There are no lights in the scene. Okay, so let's compile this file. We already had that warning. This is not important, however. Then let's go to the symbol scene. Let's compile it. There is no class named CLRT lights. Where is it? Yes, we should use this here, and also why not, because it might look better. Let's go to a position that is a bit closer and looks at the cube from a different angle. So okay, I've compiled it. Now let's render the scene, see what it looks like. And hopefully now everything works. So I'm still waiting for the rendering process to complete. Okay, there we go. Open the file, I get it for you. Yeah, there, nice. There we have our cube. We have also checked that moving our camera around works. So now maybe instead of the cube, we might try and render a sphere, because on the cube you really couldn't see the effect of the specular lighting. So let's go here, comment this out, and instead say object scene. Yeah, now I'm going to define that scene directly, that sphere directly here. Make instance of CLRT objects sphere, and its center. We can copy that line here. Whoops. What have I done? Okay, so now let's copy that line. This is our center, and the radius will also be 40. Okay, yeah, we have that. Let me compile it. Material must be specified, of course. Now we need that as well. Material will be the blue material. Compile it. And you know what? Why not also go to the scene so that we get a little bit output at least. And let's say here, let's say something like every 40th row we display a message, how much we about the percentage that we have already completed the resulting image. So when 0p mod y equal 40, we say format t rendering, and what we will display is the percentage, so the 2f. Okay, that's it, and the percentage is actually, or no, we'll just display it as an integer. So, and this is the result of y times 100 divided by the height, if I'm not mistaken here. Okay, I'll compile that. Yep, go back to the simple scene, compile that, and let's render. See what it looks like. At least we don't get any output. This is not what we wanted. Yeah, no, there we get it. So yeah, let's open the image, and this looks rather nice. Here you can see the effect of the specular lighting and our sphere. Yeah, okay, here it's dark because we have no light. We could also increase the value of the ambient color and get more lighting instead. However, I'm quite satisfied with the result, and yeah, let me show you what we'll do during the next part. I'll give you a preview on that part. We'll be doing transformations like rotation, scaling, and translation. Also, to improve the speed, we're quite slow now. We'll be using axis-aligned bounding boxes. Quite easy, this particular topic. And yeah, maybe we'll come to the point where we do recursive ray tracing, but for that I'd also have to introduce reflections and refractions. However, we'll see what time brings. Yeah, and this image now here concludes this part 2.1 of the tutorial. Thank you very much for listening. Once again, sorry for the error. Yeah, thank you. Bye.